Hello, my friend. There are few ideas more fundamental than the fate of the universe itself. Everything we know exists inside this vast cosmic story, and tonight we are following it all the way to its final chapter. But the ending may not be what you expect, because the universe has more than one way to disappear, and each possibility reveals something profound about reality. Hidden inside this question are mysteries about time, space, matter, and the quiet rules that hold everything together. If falling asleep has been difficult lately, then you are in the right place. Let the noise of the day fade, and together we will travel toward the deepest future science can imagine. Chapter 1. The universe is already changing toward an ending. Few ideas are more quietly astonishing than this one. The universe is not simply existing around us, but slowly moving toward a final state. When people imagine the end of the universe, they often picture a sudden catastrophe, some enormous explosion or collapse that arrives like the last scene of a film. Modern cosmology suggests something stranger and, in a way, more profound. The end of the universe is not only a future event. In an important sense, it has already begun, because the processes that will shape the final fate of everything are already underway. The universe is changing now. Space is expanding now. Stars are burning through their fuel now. Galaxies are evolving now. Energy is spreading out, structure is aging, and the cosmos is moving along the long one-way journey that began with its birth and will continue far beyond anything human beings will ever witness directly. To understand this, it helps to begin with a simple idea. The universe is not a collection of objects sitting motionless inside a fixed, empty box. It is a dynamic system. On the largest scales, the fabric of space itself changes with time. For more than a century, astronomers have learned that distant galaxies are, on average, moving away from one another because space is expanding. This does not mean that every galaxy is flying through space in the ordinary sense like shrapnel from an explosion. It means that the distances between great cosmic structures tend to grow because the stage on which the universe exists is stretching. The universe of today is not the universe of the distant past. It is larger, colder, more diffuse, and more evolved. That alone already tells us something important. A universe that changes in one direction for long enough cannot remain forever as it is now. If expansion continues, then matter becomes more spread out. Gas clouds become less able to collapse into new stars. Regions of space that are not gravitationally bound drift farther apart. Light traveling through expanding space loses energy as its wavelength is stretched. The general trend is not toward greater concentration, brightness, and activity, but toward thinning, cooling, and separation. The night sky still contains stars because we live in a relatively early era when the universe remains rich in structure and free energy. But this is not a permanent condition. It is a phase. Another deep clue comes from thermodynamics, the branch of physics that studies energy, heat, and change. One of its central ideas is that, in an overall sense, natural processes move toward states in which usable energy becomes less available. This is often described with the concept of entropy. The word can be misleading if treated too casually, but in broad terms it points to the fact that energy tends to spread out, differences tend to even out, and ordered situations do not maintain themselves forever without a source of fresh energy. A hot cup of tea cools in a room. It does not spontaneously become hotter. A bright star radiates energy into colder space. It does not gather that same energy back into itself. On cosmic scales, the same principle matters enormously. The universe can still host stars, planets, weather, chemistry, and life because it is not in thermal balance. There are still gradients, still differences, still places where energy can flow from more concentrated states to less concentrated ones. But every such process uses up part of that opportunity. This is why the end of the universe is not mainly about destruction in the dramatic sense. It is about exhaustion, not the disappearance of all matter in a single moment, but the gradual loss of the conditions that make interesting things happen. Stars shine because gravity squeezes matter together until nuclear fusion begins in their cores. That fusion releases energy, and that energy pours outward as light and heat. Yet every star lives by spending a finite reserve of fuel. Massive stars burn furiously and die relatively quickly. Smaller stars burn much more slowly and can last vastly longer. But none of them are eternal in the ordinary sense. Every star is an engine running down. Since stars are the great makers of light, warmth, and chemical complexity, their finite lives tell us that the universe is living through an age that cannot last forever. Even more important, stars are not appearing at the same rate forever. In many galaxies, the great age of star formation is already behind them. Galaxies need cold gas to make new stars. Over time, some of that gas is used up, some is heated, some is blown outward by stellar explosions or active black holes, and some becomes locked away in dim remnants. The universe once formed stars much more actively than it does now. That means we are not living at the energetic beginning of cosmic history, but after its peak. The cosmos is still beautiful and bright, but it is already aging. In a very real sense, we inhabit a universe after noon rather than at dawn. Expansion makes this picture even more striking. Observations indicate that the expansion of the universe is not merely continuing, but accelerating. Something in the large-scale behavior of the cosmos, often grouped under the name dark energy, appears to be causing distant regions of space to separate faster over time. This does not tear apart galaxies or solar systems under present conditions, because gravity and other forces hold local structures together. But across immense distances, the overall effect is powerful. The long-term consequence is a universe in which more and more of the cosmos slips beyond observational reach. Far future observers, if any exist, would see a darker and lonelier sky. Galaxies outside their local gravitational neighborhood would recede so far that their light would no longer reach them. The universe would not only be aging, it would be becoming more isolated. This matters because cosmic endings are shaped not only by what objects are made of, but by how they are arranged and whether they can still interact. A universe full of matter is not necessarily a lively universe. Activity requires contact, contrast, and available energy. If matter becomes too dispersed, if light fades, if fuel is exhausted, and if distant structures can no longer influence one another, then the stage for complexity begins to empty. The laws of physics may remain the same, but the opportunities those laws allow become narrower. It is the difference between owning musical instruments and still having musicians, electricity, and air in the room. The ingredients might remain, but the performance ends when the conditions that sustain it disappear. There is also a subtle but beautiful point here. The universe began in a state that was, in a crucial sense, highly special. It was hot, dense, and remarkably uniform on large scales, yet it also contained tiny irregularities. those small unevennesses allowed gravity to build structure over time. Galaxies formed, stars ignited, planets assembled, and the chemical elements made in stellar interiors became part of new systems. In other words, the richness of the present universe emerged because the early universe was not in its final, exhausted state. It still had room to unfold. It still had a future full of possible structure. The fact that anything complex exists at all tells us that the cosmos began far from equilibrium. We live in the long aftermath of that initial condition. So when we ask how the universe ends, we are really asking how that stored potential is gradually spent. We are asking how long structure can resist dispersal, how long stars can keep converting mass into radiation, how long galaxies can keep their remaining gas, and how long physical differences can continue driving change. These are scientific questions, not only philosophical ones. They can be studied through observation, through theory, and through the laws already known to describe gravity, matter, radiation, and thermodynamics. The answer is not fully settled in every detail, because there are still profound mysteries, especially about dark energy and the ultimate behavior of matter over unimaginable timescales. But the broad direction is clear. The universe is not static, not cyclical in any confirmed everyday sense, and not suspended in a timeless balance. It is evolving from a more active state toward a less active one. That perspective can feel unsettling at first, because human beings naturally think in terms of endings as losses. But cosmic time changes the mood of the question. The universe is not on the verge of shutting down. The great stars still shine, new stars still form, galaxies still turn, worlds still orbit. Life still has room to emerge, think, and wonder. The important point is not that the ending is near, but that change itself is fundamental. The universe has a history, and because it has a history, it also has a direction. The conditions we see around us are not permanent features of reality. They belong to a chapter. In this video, that is where we begin. Before exploring the specific scenarios that may define the far future, we need to see that the ending is not an alien interruption imposed on an otherwise finished cosmos. It grows naturally out of the universe we already inhabit. Every ray of starlight leaving a star, every galaxy drifting farther away, every cloud of gas turning into new suns and then slowly running out, every increase in the spreading of energy across space is part of the same long story. The end is not separate from the present. The present is how the end begins, and for now, that is enough to hold gently in mind. The universe is vast, patient, and still full of light, and you do not need to carry all of cosmic time at once. You can simply rest inside the thought that everything moves in seasons, even the stars. And tonight you are allowed to be still while the universe continues its quiet journey. Chapter 2. The Big Freeze, the slow fading of everything. Of all the endings physicists have imagined, the Big Freeze is the quietest, the most haunting, because it does not arrive as a single disaster. It arrives as a long surrender of light, warmth, motion, and possibility. The universe does not end with one final explosion or one final collapse. It simply keeps expanding, and as it expands, the conditions that allow stars to shine, galaxies to grow, and life to flourish gradually disappear. The universe appears to be getting larger, and the larger it becomes, the more spread out everything becomes on the greatest scales. Matter that was once relatively close becomes more separated. Radiation stretches as space stretches. Energy becomes less concentrated. over immense lengths of time, this changes the character of the cosmos. A young universe is crowded, energetic, and full of raw material. A much older universe is thinner, darker, colder, and less active. The Big Freeze is the name for that long transformation carried to its farthest limit. To understand why this happens, it helps to think about what makes the present universe lively. Stars shine because dense clouds of gas can collapse under gravity, heat up, and begin nuclear fusion. Galaxies remain rich and structured because they contain matter that can still interact, collide, cool, and reorganize. Planets can have weather, oceans, and chemistry because they receive energy from nearby stars and radiate that energy back into space. Life can exist because it lives inside these flows of energy, never in perfect balance, always between a source and a sink. The universe we know is active because it is full of differences. There are hot places and cold places, dense places and empty places, bright regions and dark ones. These differences allow change. The Big Freeze is what happens when those differences slowly fade. This does not mean that every difference vanishes all at once. It means that the great engines that maintain cosmic structure eventually lose the ability to renew themselves. The first important step in that direction is already visible. The universe is still making stars, but not at the furious rate it once did. The era of most intense star formation happened long ago. Many galaxies have already used a great deal of their cold gas, the raw material from which new stars are born. Some of that gas has been locked into stars. Some has been heated so much that it no longer collapses easily. Some has been blown outward by stellar explosions or by the violent activity around supermassive black holes. As a result, the universe is still luminous, but it is no longer at its brightest age. That decline matters because stars are the main source of long-lived order in the visible universe. They light planets, drive chemical cycles, create heavy elements, and shape the structure of galaxies. If fewer stars are born, then the future contains fewer sites where complexity can emerge. Over long timescales, existing stars continue to age and die, while the supply of fresh replacements becomes smaller. The universe does not switch off. It grows dimmer generation by generation. Different stars fade in different ways. Very massive stars live fast and die young, ending as spectacular explosions or collapsing into dense remnants. Medium stars like our Sun live much longer and end more gently, shedding their outer layers and leaving behind hot stellar cores that cool over time. The smallest true stars burn their fuel so slowly that they can survive for astonishingly long periods. These red dwarfs are likely to be the last ordinary stars still shining in the far future. But even they are not eternal. The important point is that the universe can delay darkness for an extremely long time, but it cannot avoid it forever if no endless source of new fuel appears. The expansion of space reinforces this fading. On the largest scales, galaxies that are not bound together by gravity continue to move farther apart as the universe grows. Groups and clusters of galaxies can remain together locally if their gravity is strong enough, but beyond those bound systems, the general trend is separation. In the far future, a typical galaxy group may find itself increasingly isolated, surrounded by distances so immense that light from the rest of the universe can no longer cross them in any useful way. Future observers would not only see a darker sky because stars are aging, they would also see an emptier one because more of the universe would lie beyond reach. As the universe expands, light itself changes. When radiation travels across expanding space, its wavelength is stretched. This lowers its energy. Over long periods, the leftover glow from the hot early universe becomes ever colder and weaker. Starlight emitted by distant sources is also shifted toward lower energies as it travels through the expanding cosmos. The universe is not simply filling with more darkness because stars run out. It is also becoming a place where radiation is diluted and cooled by expansion itself. Thermodynamics gives the Big Freeze its deepest foundation. The universe still contains enormous amounts of energy, but what matters for structure and activity is not only the total amount. What matters is whether that energy is available in forms that can do work, drive motion, or maintain organized systems. A star is useful in this sense because it concentrates energy and releases it into a colder environment. A planet with a warm interior and incoming starlight can sustain changing conditions because there are gradients, differences, and flows. But when energy becomes more evenly spread, less of it remains available for interesting processes. The universe drifts towards states in which change becomes harder to sustain. This is why the Big Freeze is often associated with the idea sometimes called heat death, though the phrase can sound more dramatic than the physical picture really is. It does not mean the universe becomes hot and dies. It means that the universe moves toward a state in which there are too few usable energy differences left to power complex processes on a large scale. Imagine a world in which every battery is nearly flat, every fire has burned low, and every engine has almost no fuel left to turn. The materials may still exist, but the capacity to make them do anything significant has largely drained away. In the far future envisioned by the Big Freeze, the bright age of stars gives way to an age dominated by remnants. White dwarfs cool into darker objects. Neutron stars slowly lose their heat. Black holes remain as some of the most persistent structures in the cosmos. Planets without starlight become frozen worlds drifting around dead stars or wandering freely through darkness after gravitational encounters disturb their old orbits. Galaxies themselves change character. Instead of glowing collections of active stars and nebulae, they become graveyards of dim remnants. Even then, the story does not end quickly. The Big Freeze is not a sudden blackout, but an extreme stretching of time. Processes that seem permanent on human scales are temporary on cosmic ones, and processes that feel almost unimaginable to us can still be brief compared with the lifespan of the universe as a whole. Matter may remain bound in remnants for lengths of time so vast that ordinary language struggles to hold them. Black holes, especially the largest ones, may dominate the deep future for enormously long eras before even they begin to fade through slow quantum processes. The Big Freeze is therefore not a single moment, but a chain of eras, each dimmer and more sparse than the one before. There are still uncertainties in this picture, and it is important to be honest about them. The Big Freeze depends on the long-term behavior of cosmic expansion, which is linked to whatever dark energy truly is. If dark energy remains similar to what observations currently suggest, then continued expansion makes the freeze-like future a strong possibility. But some details of the remote future depend on questions that are not fully settled, such as whether ordinary matter is absolutely stable forever, and how certain extreme processes behave over inconceivably long timescales. Even with these uncertainties, the broad direction remains clear. Continued expansion, declining star formation, stellar aging, and the spreading out of usable energy all point toward a cosmos that becomes less active rather than more. What makes the Big Freeze especially powerful as an idea is that it changes what we mean by the word end. Usually, an ending sounds like a final event, a boundary that is crossed once and for all. The Big Freeze suggests something more gradual and more universal. The end is the slow disappearance of the conditions that make the universe feel alive. There may still be objects, there may still be matter, radiation, and gravity, there may still be isolated events, but the grand age of light, formation, and transformation gives way to an age of persistence without renewal. And yet this future, for all its darkness, should not be misunderstood as a tragedy unfolding tomorrow. The universe still has immense reserves of time ahead of it. Stars will continue to shine for ages beyond anything human history can measure. Galaxies will continue to turn. Worlds will continue to exist. The Big Freeze matters not because it threatens us soon, but because it reveals the direction of cosmic time. It tells us that the universe is not a static backdrop. It has an arc. It has youth, maturity, and old age. There is something strangely calming in that idea. The night sky feels timeless when we look up at it, yet it is part of a story, and stories move. The stars above us belong to an era of brightness that will not last forever, but that does not make it less beautiful. It may make it more so. For now, the universe is still full of warmth, structure, and light, and you are here during one of its most luminous chapters. You can let that thought soften the edges of the day and simply rest for a while inside this brief, bright moment of cosmic time. Chapter 3. When the last stars die. The Big Freeze becomes truly real when we stop thinking about the universe in the abstract and picture a concrete change. One day, somewhere in the unimaginable future, the last stars will finish shining. That moment will not happen everywhere at once, and it will not arrive as a final dramatic flash. It will come through a long thinning of starlight across cosmic time, until the universe passes out of its age of light and into something darker, quieter, and far less fertile than the cosmos we know now. Stars are the great makers of order. They are not just lights in the sky. They are furnaces that create many of the chemical elements needed for rocky planets, oceans, atmospheres, and living bodies. They warm planets, drive weather, and provide steady flows of energy that chemistry can build upon. The universe with stars can be active, structured, and creative. A universe without stars is still a universe, but it is no longer one that easily renews itself. To understand how the last stars die, it helps to remember that stars are not all the same. Their lives depend above all on their mass. The most massive stars burn through their fuel with astonishing speed. They are brilliant, hot, and short-lived. Smaller stars are dimmer, cooler, and far more patient. They burn their fuel much more slowly and can survive for lengths of time that make even the present age of the universe seem young by comparison. This means the final age of stars will not belong to giant blue stars or to stars like our sun. It will belong mainly to the smallest true stars, the red dwarfs. A red dwarf is easy to underestimate. It is small, faint, and modest compared with a large star. But in the far future, those modest stars matter more than any others. Inside them, energy production proceeds slowly and efficiently. Their interiors can mix material in a way that lets them use a very large fraction of their hydrogen fuel. Because of that, they can keep shining for immensely long periods. Long after larger stars have died, many red dwarfs will still be there, glowing weakly but steadily. In the last stellar era, the universe will likely be lit not by grand suns, but by countless dim embers. That future also tells us something about life. If life exists elsewhere and survives for very long stretches of cosmic time, then some of the longest opportunities for it may lie around small, long-lived stars. A planet orbiting a calm red dwarf could, in principle, remain in a region warm enough for liquid water for a very long time. That gives nature one thing it may need most: time. Biological complexity may require not only the right conditions, but also enough stability for those conditions to persist. In that sense, red dwarfs may seem like promising homes for life in the deep future, but they are not gentle stars in every way. Because red dwarfs are dim, planets must orbit close to them to receive enough warmth. That closeness can create serious problems. Young red dwarfs can be highly active, producing frequent flares and bursts of high-energy radiation. A nearby planet may have its atmosphere eroded or chemically altered. Tidal locking may also occur, leaving one side of a planet turned toward the star for very long periods, though that does not automatically make life impossible. Thick atmospheres or oceans might still move heat around. So the future of life around red dwarfs is a complicated picture. These stars may offer the longest-lasting lamps in the universe, but not necessarily the easiest worlds on which life can begin or endure. Over time, even the red dwarfs will change. They do not last forever. Their great gift is longevity, not immortality. As they slowly consume their hydrogen, their brightness and internal structure evolve. The smallest stars are expected to end quietly, leaving behind dense remnants rather than exploding. The universe can delay darkness for an extraordinarily long time, but it cannot avoid it forever if no new long-lived stars keep appearing to replace the old ones. By then, star formation itself will have nearly ended. The cold gas needed to build new stars will be depleted, heated, scattered, or locked away in old objects. The remaining stars will mostly be survivors from earlier eras. Every death will reduce the number of active lights, and there will be very few newborn stars to replace them. That is what makes the death of the last stars so different from stellar death today. In the present universe, stars die inside galaxies that are still rich with other stars and, in some places, still capable of making new ones. In the deep future, a dying star is part of an irreversible decline in the total number of luminous engines left in existence. As the final stellar populations age, galaxies themselves change character. Spiral arms, bright nebulae, and star-forming clouds become relics of an earlier epoch. What remains is a quieter gravitational society of old stars, white dwarfs, neutron stars, brown dwarfs, planets, and black holes. Encounters between objects can still happen. Orbits can still shift. In especially crowded regions, some remnants may be thrown out into interstellar or even intergalactic darkness. But these are rearrangements of leftovers, not signs of renewal. The galaxy of the far future is not dead in the sense of being empty. It is old in the sense of being unable to make much that is new. The last ordinary stars may not mark the absolute last source of light. Even after the main age of stars has ended, there can still be occasional flashes. Dense remnants in close pairs may interact. White dwarfs can pull matter from companions under the right conditions. Collisions between remnants may release bursts of energy. Gravitational encounters might push objects together that were once widely separated. So darkness does not arrive as a perfectly smooth curtain. There may be rare sparks or brief episodes of renewed brightness. This raises another question about life. Could life survive after the main era of stars, perhaps around stellar remnants rather than ordinary stars? The answer is uncertain, but it is not obviously no. A white dwarf begins as a hot remnant and then cools slowly over time. In principle, a planet at the right distance could experience a period when temperatures might allow liquid water. Some scientists have explored whether such systems could host habitable environments if suitable planets were present, and if those planets either survived earlier violent stages or arrived later. But the difficulties are serious. The suitable zone would be very close to the remnant. Tidal effects could be strong, and the earlier history of the system may have been destructive. It remains an intriguing possibility, but not a simple refuge. Brown dwarfs add another layer to the picture. These are objects too small to sustain long-term hydrogen fusion like true stars. They glow faintly, mostly from stored heat, and cool with time. They are not likely to be major long-term havens for life as we understand it, but their existence reminds us that the far future universe will be populated by many dim bodies that do not completely vanish, yet do not truly illuminate their surroundings either. The cosmos after the last stars is not pure nothingness. It is a landscape of cold survivors. There is also a deeper meaning in the death of the last stars. Stars do more than shine. They maintain temperature differences, release usable energy, and create environments where chemistry can become rich and layered. Around them, planets can remain active, and perhaps minds can look back at the sky. When the final stars die, the universe loses not only its lamps, but many of its last natural settings for sustained complexity. Matter remains, but much of it is trapped in colder, dimmer, more inert forms. Yet the death of the last stars would not mean that time stops. Human intuition ties endings to final moments, but cosmic endings are usually transitions between eras. After the last stars die, the universe continues. Gravity still shapes motion. Black holes still exist. Remnants still cool. Rare encounters still occur. Extremely slow processes continue in the background. The cosmos does not shut its doors. It simply enters a new age in which light, warmth, and creation are vastly rarer than before. From the perspective of any being still around, the sky would be transformed. There would be no familiar constellations drawn by ordinary stars. There would be no new dawns on worlds that depend on stellar sunlight. If some civilizations found ways to survive around remnant objects, their relationship to the universe would be profoundly different from ours. They would live after the age that produced most of the beauty we associate with the heavens. And still, even this is not a reason for despair. The last stars die only after spans of time so vast that the present universe remains, by comparison, richly alive. We live in a cosmos where starlight is still common, where galaxies still glitter, and where the chemistry made in long-dead stars can still become oceans, forests, and thought. The eventual darkness of the far future does not empty the present of meaning. If anything, it frames our era more clearly. We live during the long, luminous middle, when the universe is old enough to have become complex, but still young enough to shine. So the chapter of the last stars is both an ending and a revelation. It tells us that even the most durable sources of light are temporary. It tells us that the future belongs first to the smallest stars, then to remnants, and finally to deeper darkness. And it tells us that life, if it persists far into cosmic time, may need to adapt to stranger and dimmer homes than any world we have known. For now, though, the sky is still full of fire. You can let that be enough tonight. The stars are still here, still quietly burning across the dark, and for a little while longer, the universe remains a place where light is ordinary. Chapter 4: The Age of Black Holes. After the last ordinary stars have faded, the universe does not become empty. It enters a new era ruled by the objects that once seemed like rare cosmic monsters. Black holes, which in our own age are only one part of a rich and luminous universe, become some of the most important structures left. They inherit the long afterlife of the cosmos. A black hole is not a hole in the ordinary sense. It is a region of space where matter has been compressed so strongly that gravity becomes overwhelming. If something crosses the boundary around it, called the event horizon, it can no longer return to the outside universe. Light itself cannot climb back out once it has passed that limit. This makes black holes deeply strange because they are among the most influential objects in the universe, while also being almost perfectly dark. We do not usually see a black hole directly. We see its effects on nearby matter and on the motion of stars and gas around it. In the current universe, black holes come in different scales. Some form when massive stars collapse at the ends of their lives. Others grow much larger through mergers and by swallowing matter over time. At the centers of galaxies sit supermassive black holes, millions or billions of times more massive than the Sun. These central black holes can shape the history of whole galaxies by affecting how gas moves, how stars form, and how energy is released into surrounding space. In the far future, that balance changes. The age of black holes begins because black holes are exceptionally durable. A star shines by spending fuel. A white dwarf and a neutron star slowly cool. But a black hole is different. Once formed, it can persist for lengths of time so vast that nearly every familiar object disappears before it does. This does not make a black hole immortal, but it does make it one of the last major forms of organized matter to survive the fading of the stellar universe. That future is not bright. Black holes are powerful, but power is not the same as visibility. A black hole with no matter falling into it is almost silent. It does not blaze on its own. In the present universe, some black holes appear brilliant because gas falling inward becomes heated to extraordinary temperatures before crossing the horizon. The light comes from that infalling matter, not from the black hole itself. In the deep future, gas becomes scarce. The rich clouds that once fed stars and active galactic centers are largely gone. As a result, many black holes may spend immense stretches of time in near darkness, influencing their surroundings gravitationally, but producing very little light. So why call it the age of black holes at all? Because they increasingly become the main long-lived anchors of structure. In old galaxies, the brightest actors are gone or nearly gone. What remains are remnants: black holes, white dwarfs, neutron stars, brown dwarfs, cold planets, and scattered debris. Among these, black holes are the objects most able to survive mergers and endure the longest. Over immense timescales, gravitational encounters slowly rearrange the contents of dying galaxies. Some objects are thrown outward into intergalactic darkness. Others sink inward through repeated exchanges of energy. Black holes, especially the heavier ones, tend to end up among the final winners of this long gravitational sorting process. In the crowded inner regions of an aging galaxy, small black holes may encounter one another or form pairs. Once two black holes orbit closely enough, they do not remain locked in a perfect dance forever. According to general relativity, accelerating masses can produce ripples in space-time called gravitational waves. Those waves carry energy away. As energy is lost, the orbit shrinks, the black holes spiral closer, and eventually they merge into a larger black hole. What was once two separate collapsed objects becomes one. In this way, the black hole population can gradually simplify itself, producing fewer but more massive survivors. Supermassive black holes at galactic centers also continue to matter in this dark future. During the bright history of galaxies, they often grew by feeding on gas and by merging when galaxies collided. In the far future, galaxy mergers become less common across the wider universe because cosmic expansion pulls large systems apart. But within gravitationally bound groups, mergers can still have happened earlier, leaving behind larger galaxies and correspondingly larger central black holes. Those central black holes may dominate the gravitational hearts of the last great galactic remnants. Yet, even a universe ruled by black holes is not a universe full of action. Most of the time, it is likely to be quiet. Black holes do not roam like cosmic vacuum cleaners, sucking in everything around them. If the sun were somehow replaced by a black hole of the same mass, Earth would continue orbiting in nearly the same way, though it would freeze without sunlight. Gravity at a distance depends on mass, not on whether that mass is a star or a black hole. The age of black holes is not a chaotic feeding frenzy in which every object is rapidly devoured. It is more like a sparse and patient era in which gravity continues to act, but opportunities for spectacular growth become rarer as matter thins out and systems settle into long-lived arrangements. Still, rare events would punctuate the darkness. A black hole passing close to a white dwarf, neutron star, or another black hole could produce a violent encounter. A remnant object torn apart by tidal forces could briefly create a hot disk of matter and a burst of radiation before disappearing behind the horizon. Two black holes colliding would release a sudden outpouring of gravitational waves. Such moments would be extraordinary, but they would be separated by enormous intervals of silence. This is where the question of life becomes especially difficult and fascinating. Ordinary life as we know it depends on long-lived, moderate energy flows, stable chemistry, and environments far gentler than the immediate surroundings of an active black hole. The region close to a feeding black hole can be flooded with intense radiation and violent tidal forces. That does not look like an inviting natural habitat. On the other hand, a black hole with matter slowly falling into it can convert mass into usable energy with remarkable efficiency. In principle, if matter were supplied in a controlled way, the environment farther from the horizon could serve as a powerful long-term energy source. This has led physicists and futurists to consider whether very advanced civilizations, if they existed in the far future, might make use of black holes rather than fear them. Such a possibility is speculative, but not pure fantasy. A rotating black hole stores enormous energy in its spin, and under certain theoretical conditions, some of that energy could, in principle, be extracted. Matter orbiting outside the horizon can also radiate strongly before it falls in. If stars become rare and ordinary sunlight disappears, a black hole that is deliberately fed with matter might function as an artificial replacement for a star. That idea should be treated carefully. Nothing in current science tells us that life will actually survive into the age of black holes, much less that it will learn to build homes around them. The conditions would be harsh, the engineering demands beyond anything humanity can currently imagine, and the available resources in the far future may be limited. But the idea matters because it reveals something subtle. A black hole is not only a symbol of destruction. In a nearly dead universe, it might also be one of the last remaining ways to maintain concentrated energy and delay complete darkness on local scales. There is another way in which black holes dominate the future. They set the timescale for what comes next. Most other familiar structures fade earlier. Black holes remain. They outlast star formation, outlast the era of luminous galaxies, and outlast the age in which most remnants are still warm. Their longevity stretches the late history of the universe into a vast, dark plateau. That next transition is tied to a revolutionary insight from quantum theory. Black holes are not perfectly eternal after all. They can slowly lose mass through a process now known as Hawking radiation. The larger the black hole, the slower this process is. For stellar mass black holes, and especially for supermassive ones, the timescales are so enormous that the age of stars seems brief by comparison. But slow is not the same as never. Even the grand rulers of the late cosmos are temporary. So the age of black holes is a middle ending, not the final one. It is the era in which the universe becomes ruled by objects that are almost invisible, immensely long-lived, and shaped by pure gravity more than by light. It is quieter than the age of stars, darker than the age of galaxies, and more patient than any era before it. If any islands of activity remain, they do so in the shadow of black holes. For now, though, black holes are still only part of a much brighter universe. They sit in galactic centers, hide in binary systems, and drift through star-filled space while the skies remain full of ordinary light. That is the strange comfort of cosmic perspective. Even the age of black holes belongs to a future so distant that tonight the universe is still luminous, still structured, and still warm enough for wonder. You can let the darkness at the end remain far away and simply rest beneath the brief bright era that came before it. Chapter 5: The Final Evaporation. When even black holes disappear. There is something especially unsettling about the idea that even black holes, the darkest and most stubborn survivors of cosmic history, do not last forever. In the previous age of the universe, stars were the great engines of light. In the age that follows, black holes inherit the long future. But they are not the final state either. If the laws of physics we currently understand continue to apply across the deepest reaches of time, then even these objects slowly fade away. At first, this sounds impossible. A black hole seems like the perfect cosmic trap. Matter falls in and does not come back out. Light cannot escape once it crosses the event horizon. In ordinary general relativity, a black hole looks like a one-way boundary. A region that can swallow but not emit. Then quantum theory changed the picture. The key insight is that empty space is not truly empty in the deepest physical sense. On very small scales, the vacuum has structure. Quantum fields still exist even where no ordinary particles are present. When the physics of quantum fields is considered near the event horizon of a black hole, the result is startling. A black hole can have a temperature, and anything with a temperature can, in principle, radiate energy. This is the origin of what is called Hawking radiation. In many popular explanations, it is described through pairs of short-lived particles appearing near the event horizon, with one escaping and the other falling inward. That picture is useful as a first intuition, but it is not the full story. The deeper idea is that the presence of the horizon changes the quantum state of the vacuum in such a way that an outside observer sees a faint flow of radiation coming from the black hole. The important point is simple, even if the full mathematics is not. A black hole is not perfectly black. That faint radiation carries energy away. Because mass and energy are linked, the black hole slowly loses mass as it radiates. In other words, it evaporates. The word can feel strange because we usually think of evaporation as water leaving a puddle in sunlight. But the logic is similar in spirit. Something that once seemed stable gradually leaks away. The difference is that black hole evaporation is unimaginably slower for ordinary astrophysical black holes than any everyday process we know. This slowness matters. A black hole formed from a collapsed star does not disappear anytime soon. A supermassive black hole at the center of a galaxy lasts vastly longer still. In fact, the larger a black hole is, the colder it is, and the more slowly it radiates. That means the greatest black holes are the most patient objects in the known universe. While stars die, remnants cool, and galaxies fade, black holes remain. Yet slow is not the same as eternal. If a black hole is not gaining new mass, and if the surrounding universe keeps cooling, then eventually its tiny outward leak matters more than any incoming energy. Over a long enough time, the black hole shrinks. As it shrinks, something surprising happens. It gets hotter. A smaller black hole radiates more strongly than a larger one. So evaporation is not a steady fade at one constant pace. It begins almost imperceptibly, then gradually accelerates. The last stages are expected to be far more violent than the first. For immense stretches of time, black holes barely seem to change. They sit in darkness, perhaps with no nearby matter left to feed on, losing mass at a rate so tiny that it would be meaningless on any human or even stellar timescale. But over much longer spans, the balance shifts. The black hole becomes smaller, hotter, and brighter. In its final phases, it may release a much more intense outpouring of radiation before disappearing entirely. There is an important note of caution here. Physicists are confident about the broad idea that black holes radiate and lose mass, but the exact details of the very last instant remain uncertain. That is because the final stage may involve conditions where our current theories, which combine quantum effects with a classical description of spacetime, are no longer enough. A full theory of quantum gravity does not yet exist in complete tested form. So while the long evaporation story is well motivated, the precise last moment is still an open question. Even with that uncertainty, the overall meaning is clear. Black holes are not the permanent endpoint of cosmic history. They are a long chapter, perhaps the longest, but still a chapter. After the great age of stars, and after the quieter age in which black holes dominate what remains of structure, the universe proceeds into an even thinner future where the black holes themselves are gone. What would the universe look like then? By that stage, it would be extraordinarily dark and diffuse. If black holes also disappear, then the remaining universe is left with a sparse sea of low-energy radiation and whatever stable particles still survive. If protons eventually decay, as some theories allow, though this has never been observed, then ordinary matter itself may not remain forever. If protons are absolutely stable, then some matter could persist in extremely cold and isolated forms. Either way, the universe after black holes is not rich with structure. This future is one of the purest expressions of thermodynamic exhaustion. Earlier in cosmic history, the universe contained many places where energy differences could drive events. Stars shone into cold space. Planets received warmth from suns and shed it outward. Matter fell into gravitational wells and released energy. Black holes themselves, despite their darkness, still represented concentrated mass and organized structure. But once even black holes are gone, the opportunities for further change become smaller still. This raises a difficult and fascinating question about life. Could anything alive survive into the age when black holes are evaporating? For ordinary biology, the answer is almost certainly no. The environments we know require chemistry, moderate temperatures, and sustained energy gradients. Those conditions belong to much earlier eras. But if one allows the possibility of very advanced forms of life or machine-based civilizations, the picture becomes less simple. A black hole that is evaporating is also radiating. In principle, radiation is energy, and energy can be used. In the very distant future, when stars are gone, an evaporating black hole could be one of the last remaining concentrated power sources in the universe. Some physicists have pointed out that a very small black hole would emit much more strongly than a large one. That leads to a remarkable thought. Perhaps an advanced civilization might, in principle, gather around an appropriately sized black hole and use its radiation as a source of power, much as life on Earth uses sunlight. This idea is highly speculative, and there is no evidence that any civilization has ever done such a thing. There are serious problems, of course. A black hole hot enough to provide substantial energy would also emit harsh radiation. The engineering required to live safely near it would be beyond anything currently imaginable. A naturally occurring black hole of the right size might not exist where or when needed. And if such a civilization had to build or transport a tiny black hole, the technical challenges would be extraordinary. Even so, the idea reveals something profound. The very process that destroys a black hole might briefly make it useful. There is another reason the final evaporation of black holes matters. It sharpens one of the deepest unsolved problems in modern physics. What happens to information? If matter falls into a black hole, and the black hole later evaporates into thermal radiation, what becomes of the detailed information that described the matter that fell in? Many physicists believe information is not truly destroyed because the laws of quantum theory are built around that assumption. But how exactly the information survives or is encoded remains one of the great puzzles. There is also a quiet beauty in the logic of all this. The universe is consistent enough that even its darkest objects participate in change. Nothing is allowed to stand completely outside time. Not stars, not galaxies, not black holes. The cosmos keeps moving, era after era, each one giving way to the next. And still, none of this is close to us. The timescales involved are so vast that the whole history of humanity disappears into insignificance beside them. Earth, the Sun, and the Milky Way in its current form all belong to an early and active chapter. The disappearance of black holes belongs to a future so remote that even calling it distant hardly captures it. By the time the last black holes evaporate, the universe will have passed through more silence than we can meaningfully imagine. There may be no stars, no planets warmed by sunlight, no galaxies shining across the dark, and perhaps no observers left to witness the final flashes. But whether or not anyone remains to see it, the logic is the same. The black holes slowly shrink, their temperature rises, their radiation grows stronger, and at last, even the great keepers of the dark let go of their mass and disappear. What comes after that is not a dramatic new beginning. It is a thinner universe still, one with even less structure, less contrast, and less opportunity for organized change. In that sense, black hole evaporation does not save the cosmos from the big freeze. It completes it. And for now, that is only a far echo of a future beyond futures. Tonight, the stars still exist, galaxies still glow, and black holes remain hidden among brighter things. You do not need to carry the whole end of time in your mind. It is enough to rest inside the strange, calm fact that even the darkest objects are temporary, and that the universe, for all its severity, unfolds with immense patience. Chapter 6. The Big Rip, if expansion turns violent. The Big Rip is one of the most dramatic endings ever proposed for the universe, because unlike the slow fading described in the Big Freeze, this scenario does not merely leave the cosmos cold and empty. It actively tears the universe apart. If it were true, the future would not be shaped mainly by exhaustion, but by a steadily strengthening expansion that eventually overcomes every structure in existence. To understand why this idea is so extreme, it helps to begin with something astronomers already know. The universe is expanding, and that expansion is accelerating. Galaxies on the largest scales are not simply moving apart because of some ancient explosive push from the beginning of time. Space itself is growing. Over the last few decades, observations have shown that this growth is not slowing under gravity in the simple way people once expected. Instead, something in the large-scale behavior of the cosmos is making distant regions separate faster over time. That unknown influence is often grouped under the name dark energy. The name is useful, but it does not mean scientists have identified a substance in a bottle or detected a familiar force with a known source. It is a label for the fact that the expansion of the universe is speeding up. The simplest interpretation is that empty space itself has an energy associated with it, sometimes described as a cosmological constant. In that case, the expansion continues to accelerate, but in a comparatively steady way. The Big Rip requires something more severe. It requires a form of dark energy whose effect grows stronger as the universe expands. That is the key difference. In the gentler picture, expansion gradually carries distant galaxies away and leaves the universe colder and more isolated. In the Big Rip picture, the repulsive influence of cosmic expansion does not simply continue. It intensifies so much that no binding force can resist it forever. Gravity loses first on the largest scales, then on smaller ones. Galaxies come apart, star systems fail, planets are stripped away. In the most extreme version, even atoms and atomic nuclei can no longer hold together. This sounds almost like science fiction, but the idea came out of real cosmological mathematics. If dark energy has a certain kind of behavior, sometimes called phantom dark energy, then the scale of the universe can grow without limit in a finite amount of time. That phrase is important. It means there would not just be endless expansion over endless time. There would be a final era in which the growth becomes so violent that structures are destroyed in a specific sequence as the end approaches. The first things to fail would be the largest gravitationally bound systems. Galaxy clusters, which are held together by gravity across immense distances, would no longer remain stable once the outward expansion became stronger than their mutual attraction. The galaxies inside them would drift away from one another, not because they had been kicked apart in the ordinary sense, but because the background expansion would overwhelm the glue that once linked them into a single system. After that, individual galaxies would be affected. Today, a galaxy like the Milky Way is safe from cosmic expansion because its stars are gravitationally bound. Space may expand across the universe as a whole, but inside a stable galaxy, gravity wins easily. In a Big Rip future, that would eventually change. The expanding background would become strong enough to pull stars out of their orbits around the galactic center. A galaxy would no longer be a coherent island of matter. It would dissolve. Only later would smaller systems feel the effect. Solar systems, which normally ignore the expansion of the universe almost completely, would no longer be protected if the repulsive influence kept growing. At some stage, the pull that keeps a planet in orbit around its star would become weaker than the outward stretching built into space itself. Planets would drift away from their suns. Moons would leave their planets. The architecture of worlds would fail. This is where the question of life becomes especially clear. In the earlier scenarios, one could at least imagine life surviving for very long periods around the last stars, or perhaps near exotic energy sources in a dim future. The Big Rip offers far less comfort. Once star systems are pulled apart, the stable environments needed for long-lived biology disappear with them. Oceans, atmospheres, and climates all depend on gravitational order and persistent local conditions. A universe in which the bonds between worlds are being broken is not one that leaves much room for life to adapt indefinitely. Still, if the Big Rip were real, life would not notice it at first. That is one of the strangest aspects of the scenario. For almost all of cosmic history, the universe could look normal on human scales. Galaxies would exist, stars would shine, planets would orbit, civilizations, if any, might build histories under seemingly stable skies. The danger would reveal itself only in the deep future, and even then, it would begin on scales so large that local observers might first detect it only through careful astronomy. The sky beyond their galaxy would grow emptier. Distant galaxies would vanish beyond view. Only much later would the destruction move inward toward the systems that matter directly to life. As the final stage is approached, the picture becomes almost unbearable in its violence. A planet near its star would not simply freeze from lack of sunlight, as it might in other end-of-the-universe scenarios. Instead, its orbit itself would fail. If the repulsive expansion continued strengthening, then eventually gravity could no longer hold the planet together as a spherical world. Mountains, oceans, atmospheres, and solid ground all exist because forces of different kinds hold matter together across different scales. The Big Rip is the progressive defeat of all of them. In the most extreme theoretical versions, not even molecules survive. Chemical bonds depend on electromagnetic attraction between charged particles. If the outward drive of expansion becomes strong enough on small enough scales, molecules would be pulled apart into atoms. If the process continued still further, atoms themselves could not remain intact. Electrons would no longer stay bound to atomic nuclei. Matter, in any familiar sense, would stop existing as organized substance. Some descriptions go even farther and suggest that atomic nuclei themselves could eventually be torn apart if the final divergence became strong enough. Whether that last step truly occurs depends on the exact physics of the model, and this is one reason it is wise to present the Big Rip carefully. The broad idea is that structure fails from large scales downward. The exact endpoint depends on how the unknown dark energy behaves in its final approach to the rip. What makes this scenario scientifically interesting is not only its drama, but what it says about dark energy. The Big Rip is not a random fantasy attached to the end of time. It is a test of how sensitive cosmic destiny is to the properties of whatever is driving accelerated expansion. A tiny difference in the nature of dark energy can produce a profoundly different future. If dark energy is truly constant, the universe may expand forever without tearing bound systems apart. If it weakens, the long-term story could change in another direction. If it behaves like phantom dark energy, then the ending becomes catastrophic. At present, the Big Rip is not the leading expectation. Current observations are broadly consistent with dark energy behaving like a cosmological constant, which points more naturally toward continued expansion and long-term fading rather than a violent tear. But the nature of dark energy is still not fully understood, and one of the deepest tasks of modern cosmology is to determine whether it is truly constant or something more dynamic. As long as that remains unsettled, the Big Rip remains a serious theoretical possibility worth exploring. And yet even this ending, if it were true, belongs to a future unimaginably distant from us. No sign suggests that our planet, our solar system, or our galaxy is under any immediate threat from cosmic expansion. On local scales, gravity and the other known forces remain overwhelmingly stronger. The stars above us are not being pulled apart tonight. The atoms in your body are not quietly coming undone. The Big Rip, if it lies anywhere in the future at all, lies so far ahead that entire cosmic eras stand between us and its first consequences. That distance gives this chapter a strange calm. We are allowed to study even violent ideas without living inside their danger. The value of the Big Rip is not that it frightens us, but that it teaches us how much the fate of everything depends on the deep nature of empty space. The future of galaxies, worlds, and life may be written not only in stars and gravity, but in the quiet properties of the vacuum itself. So the Big Rip stands as one of the starkest possibilities in cosmology. It imagines a universe whose expansion grows so powerful that first the largest structures, then the smaller ones, and finally matter itself are torn apart. It is not the most likely end according to present evidence, but it is one of the clearest reminders that the destiny of the cosmos depends on physics we do not yet fully understand. For now, though, the universe remains beautifully intact. Galaxies still hold together. Stars still bind their planets. Matter still keeps its shape. Whatever dark energy truly is, its deepest verdict has not yet been delivered. And because of that, you can let this possibility remain where it belongs, far out in the speculative distance, while tonight the world around you is still whole, still quiet, and still gently held together. Chapter 7. The Big Crunch. Could the universe fall back inward? The Big Crunch is the great reversal, a vision of the future in which the universe does not keep drifting outward into colder and emptier space, but instead slows, stops, and begins to collapse back in on itself. It is one of the oldest and most powerful ideas in cosmology because it feels like a kind of cosmic symmetry. If the universe began in an extremely hot, dense state and then expanded, perhaps one day it could do the opposite. Perhaps the outward story of cosmic history could turn around and become an inward one. For a long time, this seemed like a natural question. Once astronomers learned that the universe was expanding, they also had to ask whether gravity might eventually bring that expansion to an end. Gravity is, after all, an attractive force. It gathers gas into stars, holds galaxies together, and shapes the large-scale web of matter across the cosmos. It seemed reasonable to imagine that if the universe contained enough matter, then the outward motion from the beginning might one day be overcome. Expansion would slow, then halt, and then contraction would begin. That is the essence of the Big Crunch. It is not an explosion, and it is not a tearing apart. It is a collapse. The distances between galaxies would no longer grow. Then they would begin to shrink. Over immense stretches of time, the whole universe would become denser, hotter, and more crowded. The sky of the far future would not grow darker as it does in the Big Freeze. It would grow brighter and more violent. Today, cosmology treats this scenario with caution. The reason is that the universe does not appear to be heading toward a simple gravitational slowdown. Observations show that cosmic expansion is accelerating, not decelerating. That means something in the large-scale behavior of the universe is counteracting gravity across vast distances. This is why the Big Crunch is no longer considered the leading expectation. But it has not lost its scientific interest, because the nature of dark energy is still not fully understood. If the thing driving acceleration were to weaken, change, or reverse its effect, then contraction could become possible again. So the Big Crunch is no longer the default ending, but it remains one of the major possibilities because the future of the universe depends on physics that may not yet be fully known. In that sense, the Big Crunch is a reminder of how much cosmic destiny hangs on the properties of empty space. If contraction ever began, it would not happen suddenly. There would be no instant moment when the sky cracked and everything rushed inward. First, the expansion would have to slow. Then, at some unimaginably distant point, the average large-scale growth of space would stop. Only after that would the universe enter a genuine contracting phase. Even then, local systems such as galaxies, star clusters, and planetary systems would not immediately notice. Just as the present expansion does not pull apart bound systems, an early contraction would first matter most on the largest scales. But over long enough time, the change would become unmistakable. Distant galaxies that had once been receding would stop moving away and begin approaching. Light from the wider universe would no longer be stretched toward lower energies by expansion in the same way. Instead, the overall compression of space would gradually raise the energy density of radiation. The universe would be moving toward a hotter state, not a colder one. This is one of the strangest parts of the Big Crunch. In the Big Freeze, time carries the cosmos toward dimness and isolation. In the Big Crunch, time carries it toward crowding and heat. The future sky would become more populated, not less. As distances shrank, interactions between galaxies would grow more common. Collisions and mergers would become increasingly frequent. Gas clouds would be compressed. New bursts of star formation could occur. Black holes would meet and merge more often. The late universe, instead of falling silent, could become active again in a harsh and unstable way. That does not mean contraction would be a return to some younger, healthier universe. A collapsing universe is not simply expansion played backward like a film in reverse. This is an important point. Entropy would still matter. Disorder would not magically decrease just because the cosmos was shrinking. Stars that had already burned their fuel would not spontaneously reassemble themselves into younger versions. Radiation already released into space would still exist. The universe would not become neatly restored. It would become denser while carrying the full thermodynamic burden of its history. That distinction matters because it changes the emotional tone of the Big Crunch. It is not a graceful rewinding to a pristine beginning. It is a crowded, heating future in which past processes continue to leave their mark. A collapsing universe could be full of violence, radiation, and catastrophic interactions, not a smooth reversal into simplicity. Still, there might be a long middle era in which contraction is not yet fatal to all local environments. If the turnaround happens slowly enough, there could be an extended age in which galaxies become more interactive and the cosmic background grows gradually warmer. But some stars and planets still exist. In principle, life could survive for part of that era. Civilizations, if any, endured that long, might observe the changing universe and realize that the great recession of galaxies had ended. They would live in a cosmos whose future looked not like a thinning darkness, but like a slow return of pressure from every direction. Could life benefit from that? Only in a limited and temporary sense. More interactions between galaxies could trigger fresh star formation in some regions, briefly creating new energy sources and perhaps new planetary systems. A contracting universe might for a while offer islands of renewed astrophysical activity, but this would come with growing danger. Galaxy collisions stir gas, ignite intense stellar birth, and can also create more supernovae, more radiation, and more disruption. The same processes that produce light can also make environments less stable. As contraction continued, the balance would worsen. The average temperature of radiation in the universe would rise as space shrank. Light traveling through a contracting cosmos would be compressed rather than stretched, gaining energy instead of losing it. That means the background radiation filling space would become hotter over time. At first, this might be subtle, but the trend would be relentless. A universe that contracts enough eventually becomes a place where the very background of reality grows less hospitable. This is where the Big Crunch becomes especially severe as a setting for life. In the Big Freeze, life struggles against scarcity. In the Big Crunch, life would eventually struggle against excess. The universe would grow too crowded, too hot, and too violent. Stable planetary climates would become harder to preserve. High-energy radiation would become more common. Dense environments would increase the chances of gravitational disruption. Whatever life existed would be fighting against a cosmic environment that was becoming steadily less forgiving. There is also the question of scale. Even if a planet remained safe for a time, no local refuge could remain independent forever in a universe whose whole background was changing. In ordinary cosmic history, local systems can often ignore the expansion of space because gravity and other forces dominate nearby. In a long contraction, that broader evolution would increasingly shape the conditions everywhere. The future would not just bring more dangerous neighborhoods. It would bring a more dangerous universe. As the collapse deepened, matter and radiation would be squeezed into smaller volumes. Temperatures would rise. Collisions between particles would become more energetic. The cosmos would begin to resemble, in some broad sense, the hot, dense conditions of the very early universe, though not in some perfectly symmetrical or simple way. The last stages of contraction are where our confidence becomes less complete. Classical general relativity, if pushed far enough, points toward an extremely dense end state, sometimes described as a singularity. But most physicists suspect that near such extreme conditions, quantum gravity would become important, and our present theories would no longer be enough on their own. That uncertainty opens the door to deeper questions. Would a big crunch end in a true final collapse? Could it lead to some sort of bounce, a new expansion, or a transition into another phase of cosmic history? These are fascinating possibilities, but they remain speculative. What matters for this chapter is the main picture. The big crunch is the idea that the universe could stop expanding and begin collapsing inward, becoming denser and hotter until the conditions of ordinary cosmic structure are lost. One reason this scenario remains compelling is that it gives the universe a different kind of narrative shape. The big freeze feels like a long fading. The big rip feels like a violent tearing. The big crunch feels like closure through return. The cosmos does not dissolve into endless emptiness. It gathers back together. There is something almost ancient in that image, as though the universe were breathing out and then, after an immense pause, breathing back in. But the poetry should not hide the physics. For contraction to happen, something fundamental about the large-scale behavior of the universe would need to allow gravity to regain the upper hand, or the influence driving present acceleration would need to change. That is why the Big Crunch is both scientifically serious and presently disfavored. It is allowed by the logic of cosmology, but not currently supported by the simplest reading of the best available evidence. Even so, it remains worth imagining because it reveals how fragile our expectations can be. A small change in the deep rules of cosmic expansion would transform the ending of everything. The same universe that now appears headed toward greater separation could, under different long-term conditions, turn around and collapse into a tightening furnace. And for now, that furnace remains only a possibility in the far distance. The galaxies are still moving apart. The night sky is not filling with returning worlds. The background of the universe is still cooling, not heating. Whatever the final fate may be, it has not yet turned toward collapse. So you can let this chapter remain what it is tonight. A profound possibility, quiet in the mind, while the real sky above you stays spacious, dark, and gently open. Chapter 8. Vacuum Decay. A sudden end no one would see coming. Vacuum decay is one of the strangest endings ever proposed because it does not depend on the universe slowly running out of fuel, being torn apart by expansion, or collapsing back inward under gravity. It depends on a more unsettling possibility that the very state of empty space may not be truly final. If that were the case, then the universe could one day change not from the outside, but from its deepest underlying structure. To understand this idea, it helps to begin with a word that sounds simple but means something very different in physics. In everyday language, a vacuum is just emptiness, a region where nothing is present. In modern physics, a vacuum is not simply nothing at all. It is the lowest energy state of the fields that fill space. This is important because the universe is built from fields. What we call particles are excitations of those fields, and the properties of matter depend on how those fields are arranged, even when no particles are present. That means empty space is not passive. It has physical properties, it has structure. It helps determine the masses of particles, the strengths of forces, and the kinds of stable atoms and chemistry that can exist. So when physicists talk about vacuum decay, They do not mean space disappearing into non-existence. They mean the vacuum itself shifting from one state to another, more stable one. The key possibility is that our universe may live in what is called a metastable vacuum. The word metastable means stable for now, but not absolutely stable forever. A useful image is a ball resting in a shallow valley that is not the deepest valley available. It can sit there for a very long time and seem perfectly settled. But if there is a lower valley somewhere beyond a barrier, then the arrangement is not truly final. In ordinary life, a ball would need a push to cross the hill. In quantum physics, a system can sometimes make a transition even without a classical shove, through a process called tunneling. This is where vacuum decay enters the story. If the vacuum of our universe is only metastable, then in principle, it could tunnel into a lower energy state. That lower state is sometimes called the true vacuum. The names can sound dramatic, but they simply mean less stable and more stable. If such a transition happened, it would not gently adjust the universe while leaving everything else mostly intact. It would create a region of new vacuum that expands outward, converting the old vacuum as it goes. This expanding region is often described as a bubble. That image is useful as long as we remember that it is not a soap bubble floating through space. It is a domain where the underlying state of the fields has changed. The wall of the bubble is the moving boundary between the old vacuum and the new one. According to the standard picture, once a bubble becomes large enough, it does not stop. It grows, and its wall moves outward at essentially the speed of light. That detail is what makes vacuum decay so uniquely final. Other end-of-the-universe scenarios unfold over huge stretches of time. Even the Big Rip, though violent in its last stages, would approach through a sequence of worsening changes. Vacuum decay offers no such warning. If a true vacuum bubble were created somewhere beyond our view, there would be no signal arriving ahead of it to announce its coming. No light, no gravitational disturbance, no messenger of any kind could outrun the bubble wall. The first sign would be the event itself, and there would be no time left to respond. Why would such a bubble be so destructive? Because the vacuum is tied to the basic rules that shape matter. If the universe transitioned to a different vacuum state, the values that determine particle masses and interactions could change. The atoms that exist now might no longer be stable. Chemical bonds might fail. Nuclear structure might change. The stars, planets, oceans, bodies, and minds built under the old vacuum could become impossible under the new one. This is one reason vacuum decay feels more absolute than many other endings. In the Big Freeze, matter remains, but energy gradients fade. In the Big Crunch, the universe may grow hotter and denser. In the Big Rip, structures are torn apart by cosmic expansion. Vacuum decay is different. It is not just an environmental disaster happening within familiar laws. It may be a replacement of the laws that make familiar structures possible in the first place. There is an important uncertainty here. Physicists can describe the general mechanism, but they do not know exactly what the true vacuum would be like, or even whether our present vacuum is really metastable. The answer depends on the deepest details of particle physics, including the measured properties of the Higgs field and the top quark, and on whether physics beyond the standard model changes the picture. Current calculations often suggest that our vacuum may be metastable rather than absolutely stable, but the issue is not closed. Small shifts in measurements or the existence of new particles and interactions could alter the conclusion. Even in the metastable case, there is no immediate reason for alarm. The most important point is that a metastable state can still last for an almost unimaginable length of time. Current estimates often place the lifetime far beyond the present age of the universe. In other words, instability in this context does not mean fragility in any ordinary sense. It means that complete permanence may not be guaranteed. That long-expected lifetime is part of what makes vacuum decay so eerie. It is not a process that gradually reveals itself. It can remain irrelevant for a span of time so vast that whole cosmic eras pass without incident. The universe can form galaxies, stars, planets, and perhaps life, all while sitting in a state that is not truly final. Everything can seem settled, and still the deeper foundation may only be temporarily at rest. The physics behind this possibility has a strong connection to the Higgs field. The Higgs field gives mass to many fundamental particles through its non-zero background value, and the shape of its potential helps determine whether the present vacuum is fully stable or only metastable. The measured mass of the Higgs boson, together with the mass of the top quark and the behavior of other interactions at very high energies, plays a central role in these calculations. What makes the story especially interesting is that our universe seems to sit close to the boundary between stability and metastability. That may be a coincidence, or it may be hinting at deeper physics not yet known. There is also a wider cosmological mystery here. The universe passed through very energetic phases in its early history, and yet the vacuum we see today survived. That fact already constrains what could have happened in the past. It tells us that whatever the true story is, our region of the universe made it through those earlier conditions without being destroyed by a fatal vacuum transition. This does not prove complete stability, but it does remind us that the universe has already endured a great deal. Could life survive vacuum decay? In the usual catastrophic version, no meaningful survival seems possible. The reason is not only that the new vacuum may destroy atoms and chemistry, but also that the transition would give no warning to observers ahead of the bubble wall. Life survives by adapting to changing environments, but adaptation requires time and information. Vacuum decay offers neither. If the advancing boundary moves at essentially the speed of light, then no civilization could observe it coming and prepare a response. The transition would simply arrive. In principle, one can imagine a milder version in which the new vacuum did not completely destroy all forms of structure. Some theoretical discussions allow the possibility that certain parameter changes might still permit organized matter of some kind. But this is not the standard intuitive picture, and it offers little real comfort. Even modest shifts in the basic constants and couplings of nature could erase the specific chemistry on which stars, planets, and biology depend. The burden of hope here is heavy, and physics gives no strong reason to expect an inhabitable outcome. This is why vacuum decay is sometimes described as the end no one would see coming. It is not because it is known to be likely, but because if it happened, it would arrive without forewarning and alter reality at the deepest level. It is less like a cosmic storm and more like the floor of existence suddenly changing its shape. And yet, there is another side to this idea, one that makes it scientifically beautiful, only frightening. Vacuum decay reminds us that empty space is not empty in any trivial sense. It has a role in the architecture of the universe. The properties of matter do not float free from the vacuum, they emerge with it. So this scenario, as unsettling as it is, reveals something profound about the kind of world we inhabit. Even nothingness in physics has structure, and that structure may have a history. It also teaches humility. We often imagine the fate of the universe in terms of the objects we can see: stars, galaxies, black holes, planets. Vacuum decay shifts attention beneath all of them. It says that the deepest question may not be what visible things do over time, but whether the stage on which they exist is truly final. Still, the honest scientific view is not one of panic. Vacuum decay is a serious theoretical possibility, but it is uncertain, deeply tied to unsettled questions in fundamental physics, and even in the metastable picture, expected to occur only on timescales overwhelmingly longer than the current age of the cosmos. That places it in a different category from immediate physical threat. It is a window into the foundations of reality, not a reason to fear tomorrow morning. So tonight, the vacuum still holds. The fields of the universe still support the atoms around you, the stars above you, and the quiet continuity of the world you know. If there is a deeper valley hidden somewhere in the structure of reality, it has not reached us, and may never do so in any meaningful future we can imagine. For now, the universe remains beautifully unchanged, and you can let that steadiness be enough as the day falls away. Chapter 9. Other cosmic endings: bounce, decay, and quantum futures. Not every possible ending of the universe fits neatly into the few famous pictures people usually hear about. Some futures imagine a slow fading into darkness. Others imagine violent tearing or total collapse. But modern cosmology also contains a quieter collection of possibilities that do not fit so cleanly into those larger categories. These are the endings that live at the edge of current understanding. Universes that may bounce instead of ending, matter that may slowly decay away, and remote quantum futures in which even an almost empty cosmos still remains physically restless. The idea of a cosmic bounce begins with a simple discomfort. In ordinary Big Bang cosmology, if we run the expansion of the universe backward, densities and temperatures rise until our current equations point toward an extreme state, often called a singularity. A singularity is not really a place we understand. It is a sign that the mathematical tools being used have reached their limit. Many physicists suspect that a complete description of the earliest universe should avoid such a breakdown. That suspicion is one reason bouncing cosmologies are taken seriously. In a bounce model, the universe does not begin from absolute nothingness in a single, unexplained instant. Instead, an earlier phase of contraction reaches some minimum condition and then turns into expansion. This family of ideas comes in more than one form. In some versions, quantum effects in gravity prevent the universe from compressing without limit and cause a rebound. In others, the universe passes through repeating cycles of expansion and contraction. There are also models in which what we call the Big Bang is not the true beginning of everything, but the transition point from an earlier state into the one we now observe. What these pictures share is the suggestion that the history of the cosmos may extend beyond the apparent beginning, and perhaps beyond the apparent end as well. If such a bounce were real, then the end of our expanding universe would not necessarily be a final ending. It could be a turning point. A future contraction might eventually lead, not to permanent collapse, but to another expansion phase. This is a very different picture from the big freeze or the big rip. Instead of drifting into irreversible silence, the cosmos might remain part of a larger repeating rhythm. Still, this should be treated with care. Bounce models are interesting and mathematically rich, but they are not established facts. The standard cosmological model, in its simplest form, does not require a bounce, and present observations do not force one upon us. Some bouncing theories face difficult problems of their own, including how to pass smoothly through extreme conditions and how to match the detailed structure we actually observe in the universe today. So the bounce remains an open possibility, not a confirmed forecast. There is also an important point about life. Even if the universe did pass through repeated cycles, that would not mean life or structure in one cycle could simply survive into the next. The conditions near any bounce would likely be so extreme that atoms, stars, planets, and biological systems as we know them could not remain intact. A cyclic universe is not automatically a universe of practical rebirth for living things. At most, it offers the possibility that endings are followed by new beginnings at the cosmic level, not that individuals or civilizations carry through them unchanged. Another family of alternative endings comes not from the geometry of the whole universe, but from the long-term stability of matter itself. Everything we touch is made mostly from atoms, and the nuclei of those atoms are built from protons and neutrons. In the standard model of particle physics, the proton is stable, but many theories that try to unify the known forces predict that protons may not last forever. No one has ever seen a proton decay, and experimental limits show that if it does happen, it is astonishingly rare. Even so, the possibility matters because the future of ordinary matter depends on it. If protons can decay, then the distant future of the universe becomes even emptier than in the ordinary big freeze picture. Planets, white dwarfs, neutron stars, cold rocks, dust grains, and the bodies of any long-dead creatures would not remain forever as silent monuments. Given enough time, the protons inside atomic nuclei would slowly transform into lighter particles and radiation. Matter would not explode. It would thin away from within, with each individual event exceedingly rare, but with enormous stretches of time making even rare events significant. This kind of ending is slow almost beyond imagination. Nothing about proton decay, if it is real, would resemble a sudden cosmic disaster. But over timescales vastly longer than the stellar era, worlds and remnants that once seemed almost eternal could gradually lose their substance. The universe would become poorer not only in light and energy gradients, but in durable matter itself. That has major consequences for long-term life. If future civilizations ever tried to survive the deaths of stars by storing themselves in cold matter, artificial habitats, or compact remnants, proton decay would place a deep limit on that strategy. It would say that matter cannot simply be kept forever as a passive library of structure and memory. The hardware of existence would itself be temporary. At the same time, the uncertainty here is important. Proton decay has never been observed. The safest scientific statement is not that protons do decay, but that some major theories allow or predict it, while experiments continue to push the lower bound on proton lifetime to astonishingly large values. If protons are in fact absolutely stable, then some matter may survive far longer than those theories suggest. In that case, the late universe could contain extremely long-lived remnants that remain intact in darkness for unimaginable durations. And even if protons are stable, the universe may still not become perfectly uneventful. Quantum mechanics has a way of preserving a kind of low-level unpredictability even in extremely cold conditions. Objects that seem frozen may still undergo very rare transitions. Tunneling processes can, in principle, allow systems to change even when classical physics would call them stuck. In the far future, when temperatures are low and ordinary activity has almost ceased, those rare processes may become some of the only remaining sources of change. This leads into what might be called quantum futures. These are not single well-established scenarios, but a group of possibilities in which the ultimate fate of the universe depends on subtle quantum behavior over enormous timescales. Some of these ideas are conservative. They simply note that quantum tunneling can permit rare changes in cold matter or extreme remnants. Others are much more speculative. They suggest that regions of space might fluctuate into new states, perhaps even giving rise to new expanding domains or baby universes disconnected from the one we know. These proposals are highly uncertain and remain far from observational confirmation, but they are taken seriously enough to be discussed in fundamental cosmology. What unites these quantum futures is the idea that emptiness is never perfectly inert. Even a universe stripped of stars, planets, and most organized structure is still a universe governed by quantum fields. And quantum fields do not behave like silent classical emptiness. They fluctuate. They allow probabilities where ordinary intuition expects stillness. That does not mean dramatic events are likely. Most quantum fluctuations are tiny and harmless. But over sufficiently vast spans of time, even very improbable events become part of the conversation. There is a famous danger here, which is that speculation can outrun evidence. A scenario can be mathematically possible without being physically likely, and physically likely without being directly testable anytime soon. So when speaking of quantum futures, honesty matters. These are not predictions in the same sense as continued cosmic expansion is a prediction. They are possibilities that arise in some frameworks once one asks what happens far beyond ordinary astrophysical history. Still, even speculative possibilities can teach us something real. They show that the fate of the universe is not only a question of stars and galaxies. It is also a question of the underlying rules of matter, vacuum, gravity, and quantum behavior. The visible universe may one day be gone, while deeper laws continue to shape what remains. In that sense, the end of astronomy is not necessarily the end of physics. Could life exist in any meaningful way in these exotic futures? The honest answer is that the prospects grow increasingly narrow. A bouncing universe does not offer easy continuity through extreme collapse and rebirth. A proton decay universe slowly erodes the material basis on which chemistry depends. A quantum fluctuation future is not a natural home for complex organisms because rare and random events are not the same thing as a stable environment. The farther one goes into these scenarios, the less the universe looks like a place where life flourishes, and the more it looks like a place where physics continues without witnesses. Yet it would be a mistake to say these ideas are only bleak. They also widen the imagination. They remind us that cosmic history may be stranger than any single ending suggests. The universe may not have one simple fate written in large letters from the beginning. Its future may depend on subtle properties of particles, fields, and space-time that we have only partly uncovered. For now, though, these other endings remain far beyond any practical horizon. Matter still holds together. The vacuum still supports the world we know. The sky is still bright with stars, and the laws that allow stable atoms and familiar chemistry are still quietly doing their work. Whatever hidden futures may exist in the deepest structure of reality, they have not arrived here. Tonight, that is enough. The universe remains in its luminous age, and you are allowed to rest inside the temporary steadiness of things. Chapter 10. Which ending is most likely and what it means for us? After exploring so many ways the universe might end, the final question is the one most people naturally ask. Which of these endings is actually the most likely? It is a fair question, but it needs a careful answer. Cosmology is not fortune-telling. Scientists do not know the future of the universe with absolute certainty because the answer depends on deep properties of dark energy, gravity, matter, and quantum fields that are still being investigated. But current evidence does allow us to say something important. Of all the major endings discussed so far, the slow fading picture known as the Big Freeze is the one most consistent with what astronomers currently observe. That conclusion rests on a simple fact. The universe is expanding, and the expansion is accelerating. On the largest scales, distant galaxies are moving away from one another, not because they are racing through a fixed empty stage, but because the stage itself is growing. More than that, the growth is speeding up. This means the universe does not presently look as though it is preparing to collapse back inward. It also does not, based on current evidence, look as though expansion is becoming wildly stronger in the way required for a big rip. The most straightforward reading of the data is that dark energy behaves in a way close to a cosmological constant, which points toward continued expansion for an immensely long time. If that picture remains true, then the universe does not end in one final event. It ends by becoming less and less capable of supporting change. Star formation continues to decline. Existing stars eventually die. Galaxies outside local bound groups drift farther away. The sky grows darker. Black holes dominate the deep future for a time, and even they eventually disappear through quantum effects. In the very long run, the universe approaches a state with very little usable energy difference left. The great drama of cosmic history gives way to stillness. This does not mean the Big Freeze has been proven. It means that among known possibilities, it is presently the leading one. The Big Crunch remains interesting, but it would require the long-term behavior of cosmic expansion to reverse from what we observe now. Vacuum decay remains one of the deepest theoretical possibilities, but it depends on unsettled questions in particle physics and quantum fields, rather than on the large-scale astronomical evidence that now points toward continuing accelerated expansion. Proton decay, too, remains hypothetical. It may deepen the emptiness of the far future if it exists, but it is not something that has yet been seen. So the honest answer is that the universe most likely ends not with violence, but with attrition. Not with one final explosion, but with the gradual loss of light, structure, warmth, and interaction. This is a quieter answer than many people expect, but in some ways it is also the more profound one. A sudden ending feels like an interruption. The Big Freeze feels like a direction. It suggests that the universe has an arrow not only in its past, but also in its future. And yet the phrase "end of the universe" can be misleading. When people hear it, they often imagine that everything simply vanishes or that existence stops in one clean moment. In the leading cosmological picture, that is not what happens. Matter may remain for extraordinary spans of time. Radiation may continue to cross space. Black holes may linger long after stars are gone. The universe continues, but in a state increasingly empty of the conditions that make complex things possible. In other words, the ending is not the disappearance of reality. It is the disappearance of opportunity. That distinction matters for what the future means for life. Life, at least in every form we currently understand, depends on energy flowing from one place to another. On Earth, life exists because our planet receives concentrated energy from the sun and releases lower quality energy back into colder space. The same general logic applies more broadly. Living systems, thinking systems, and technological systems all depend on gradients, on differences, on the fact that the universe is not in perfect balance. The big freeze matters because it is the long erosion of those differences. If we ask whether life could survive for a very long time, the answer is not a simple no. There may be windows far beyond the present era. Small, long-lived stars could support habitable worlds for vast spans of time. Advanced civilizations, if they ever arise and endure, might learn to migrate, store energy, use exotic sources, or slow their activity to stretch resources. They might move from bright stars to dimmer but longer-lived systems. Physics does not forbid intelligence from being adaptive. But physics also sets limits. No matter how clever life becomes, it cannot create usable energy differences out of nothing. It can only use what the universe provides. Over long enough spans, the supply of stars declines, matter becomes more isolated, and every strategy grows harder. The far future may allow survival for an astonishingly long time, but not necessarily forever. The meaning of the big freeze is not that life must end soon. It is that the universe does not seem arranged to support complexity without end. That can sound bleak if taken in the wrong spirit, but there is another way to hear it. The fact that the universe is not in equilibrium yet is exactly why anything interesting exists now. Galaxies formed because the early cosmos was not in its final state. Stars shine because matter can still collapse and release energy. Planets can have climates because they are bathed in starlight and cooled by space. Life can think because the universe still has gradients left to spend. A final quiet future does not make the present less meaningful. It is the reason the present is full of structure at all. This is what the likely ending tells us about our own place in time. We do not live at the beginning of cosmic history, but we also do not live near its end. We inhabit a middle age of the universe, one in which stars are common, heavy elements are abundant, galaxies still shine, and local conditions remain rich enough for living worlds. In a sense, we live during one of the most favorable eras the universe will ever offer for complexity. There's something quietly humbling in that. Human beings often imagine themselves at the center of the story, but cosmology teaches a different kind of significance. We are not central because the universe was made for us. We are significant because we are one of the ways the universe has become aware of its own history, while the conditions still allow such awareness. Long after the stars thin out and the galaxies grow lonely, the physical events will continue. But the chance to wonder about them may become rarer. The most likely ending also changes how we think about fear. When people first hear about the end of the universe, the idea can feel crushing, as though everything valuable has been placed under a sentence. But cosmic timescales are so vast that the fate of the universe is not a personal threat in any ordinary sense. The end of the universe is scientifically important, but emotionally it should be held in proportion. It is not a reason for panic, it is a reason for perspective. Perspective in this case means recognizing that finitude is not the same as futility. A star burns for a finite time, yet while it burns, it can light planets and make life possible. A civilization may be temporary, but it can still learn, build, love, and understand. The likely ending of the universe does not erase the value of what happens before it. It frames it. This is also why the more exotic endings remain worth studying, even if they are less likely. The Big Rip, the Big Crunch, vacuum decay, proton decay, and bouncing cosmologies each reveal something different about the foundations of physics. They show how much depends on dark energy, on the stability of matter, on the structure of empty space, and on the still unfinished attempt to unite gravity with quantum theory. Asking how the universe ends is therefore not only a question about the future, it is a way of discovering what the universe is right now. So if we gather everything together, the picture is this. Current evidence most strongly favors continued accelerated expansion and, with it, a long future of fading structure rather than sudden destruction. That makes the Big Freeze the most likely broad ending. Other possibilities remain scientifically meaningful, but they require new behavior from dark energy, new information from particle physics, or deeper theoretical breakthroughs that have not yet been confirmed. The uncertainty is real, but it lives inside a framework that already points in a certain direction. And what does that mean for us? It means we live in a universe whose future is probably quiet, whose beauty is temporary, and whose present is therefore precious. It means the stars above us are not background decoration, but part of a rare and finite era of cosmic possibility. It means life exists not against physics, but because physics has not yet spent all its richness. And it means that even though the universe may one day become cold and dim, tonight it is still full of warmth, pattern, and light. That may be the gentlest conclusion of all. The most likely end of the universe is unimaginably far away, and between now and then lies more time than the human mind can truly hold. For now, galaxies still glow, stars still shine, and the world around you remains gathered together in a brief, bright chapter of cosmic history. You do not need to solve the whole future tonight. It is enough to know that the universe is still here, still luminous, and that for a little while longer, so are we. And now, my friend, we have reached the end of our journey through the final futures of the cosmos. If you are still awake, you might enjoy drifting into another video and continuing this quiet exploration of space, time, and reality. But if sleep is beginning to find you, then let the stars fade softly in your mind, and let the universe carry your thoughts into rest. Thank you for spending this time with me. Sweet dreams, my friend, and sweet dreams among the stars.